Hi, everyone. My name is Riccardo. I work for AWS, and I'm a solution architect. It means that basically on a day-to-day job, I help partners and customers adopting and taking advantage of the cloud. Well, as part of the of my job and as part of the job of our other colleagues, what we do is basically we help, like I said, customers and partners adopting the cloud. And during the job, we spot some interesting cases, and while we help others, we build some patterns and we build some reference architectures to which we then open source. So we have a number of open source patterns. You can find them on GitHub if you want, and a lot of them are on Kubernetes. So today the focus of this talk is about autoscaling. What I wanted to talk to you about is autoscaling in relation to KEDA, which is the main actor here, and other components around KEDA, which are Carpenter, which is an autoscaler. Some of you might be familiar with. It's an open source autoscaler which is adopted by AWS, but also by other cloud providers, and also Prometheus and other components around it. So, like you've seen, there is a big picture here, and I'll focus on each component one by one, so we can see this specific pattern, how it is composed. Like you can see, it's basically one cluster. The cluster has been set up, in my case, quite easily on the cloud with a basic set of nodes. And I used also Flux CD for the after setting up the first set of nodes with basic components. I also used the Flux for the rest, including KEDA, Prometheus, etc. So maybe I can show you here just the small set of components that I used. We have basically one cluster folder, which is my path within the repo. If some of you is familiar with Flux CD is basically a CI/CD tool, GitOps tool that allows me to deploy into my Kubernetes cluster whatever components I need, and keep it in sync with, in this case, it's a GitHub repo that I have hosted on GitHub. And the first point, the first reference for Flux is this cluster folder. In the cluster folder, I have a list of let's say customizations, which are references. So what I was saying is that I am using Flux CD, and I'm pointing that to this cluster folder. In the cluster folder, I'm basically setting up a set of customization references that are pointing each one of them to other sections of my GitHub repo. So, for example, I have an infra section and a workload section. So in my infra section, I'm actually requesting, for example, Flux to synchronize within my cluster a number of resources which are related to monitoring. While in the workload section, which is pointed by the other customization, I am asking Flux to synchronize another set of resources which are more related to my actual deployment. And in this case, the deployment that I'm using is quite a basic application. It's a basic application that just exposes with Prometheus metrics the number of requests that it received. It's a little bit artificial because it's just for the purpose of showing how KEDA and Carpenter work together, because the number of requests that the small application exposes to fake some sort of web server is... So, like I was saying, so this is the setup, and I was talking about the small application that is running, and it's exposing just a few, well, one metric, which is the number of requests that have been received. So okay, we need to be patient a little bit. I'm sorry. I'll try to keep my hand here. Okay, so what we have here is the deployment of my container. I have a pod monitor to instruct Prometheus on what actually it should pick up, and it is referring, actually, you see, to this application. This is the path, the port, and so on. And this is the scaled object from which is actually driving. It's a custom resource from KEDA. I'll talk to you a little bit more about this. I want to first go into these details. So this is the setup. So I talked about how my Flux CD is working together with GitHub to keep in sync. Basically, what I want here is reflected into my cluster. In the cluster, by the way, I set it up with a first set of infrastructure as a code commands into Kubernetes, into Amazon EKS. But okay, again, the cluster by itself doesn't have anything. It's kind of a vanilla one, and you can set up wherever you want it. So KEDA is an event-driven autoscaler. Why would we want to use it? Is because, and we use it in a number of patterns within that we share on GitHub, like I mentioned, and the reason why we like KEDA and we use it is because it allows you to, on top of HPA, differently to HPA, we can set up a number of resources, or otherwise in KEDA terminology, scalers, that are the reference for our metrics. So KEDA pulls in metrics from these resources, and some of these sources or scalars are of very different types. Like, for example, you can have in this case here, we have Prometheus metrics, like I said. But of course, we can use others. For example, RabbitMQ, other SQS, for example, in Amazon World, or Kafka, or there are a number of scalars from different cloud providers as well. Can be also locally, or like I said, cloud provider provided. So the way it works is that, like I said, KEDA uses two features, from two perspectives. It works from two perspectives. One, it uses what's called a scaled object. There are other custom resources, like, for example, the scaled job and so on, but they basically represent the scalar or the source that I want to pull metrics from. In this case, like you can see down here, I have a snippet of the scaled object that I was showing earlier. And, well, it shows basically that I'm pulling the HTTP requests total, which is a metric which is exposed by my little application. And I am setting a threshold of 2, meaning that at the level of 2 requests, KEDA will kick in to scale my deployment in this case. Again, KEDA can work with also other resources, which also can be custom resources. In this case, I chose to use, for simplicity, the scaling of a deployment. And so I was saying that KEDA uses works from 2 perspectives. So one is to actually take the scaler and the source then of my information, and the other one is actually to make the scaling of the resource itself. So the scaled object is translated by KEDA into an HPA resource behind the scenes. This is because KEDA works in 2, let's say, 2 modes. First of all, it can drive to 0 the number of resources, my number of pods, so it can scale to 0. But that kind of scaling is managed by KEDA directly. So the KEDA operator drives the scaling from 0 to 1 and 1 to 0, which behind the scenes and does that with the scale sub-resource. The scale sub-resource, in my case, is exposed by the deployment resource, but if you're using a custom resource, it needs to expose the scale sub-resource as well if you want to use this scaling from 0, 1, and 1, 0. After 1 or from 1 to n and back, it's the logic of how the number of pods in my case is scaled is left to horizontal pod autoscaler and to the HPA resource that we see represented here by the icon. So let's see a little bit how the actual HPA resource is translated. So we are starting from basically this snippet here from the scaled object, which is a custom resource from KEDA again, and the KEDA translates that into an HPA resource, again from the scaling from 1 to n and n to 1. So you can see that it is basically very similar. It has a target with an average value of 2. In this case, I chose to use average value, meaning that the metric value that is seen by HPA will be divided by the number of pods. If that's not something which is wanted, it could be changed to value, and that will be just used as it is. The metric is exposed as with a different name, which is defined by KEDA according to some rules, some internal rules, and in this case it's S0 dash and then Prometheus. So what happens when we have when we have defined the scaled object is that we have also a HPA resource, like I said, which is generated by KEDA, and then HPA works as usual. So what it does is that it takes it makes a computation on the desired number of replicas. In my case, it's pods, by taking the basically this algorithm which you might be familiar with if you've worked with HPA before. So I have the current metric value, and it is, well, compared to the desired metric value, and then multiplied by the current replicas, and then the seal is taken. So basically, if I am actually having a metric which is quite higher, I will have a desired replicas which increases. Now, this is for the scaling of the actual workload, which is my application. I wanted also to talk to you about the scaling of the data plane. But first, maybe let's cover the other side where KEDA is operating. So KEDA is operating, like I said, on one side by defining the way we source metrics and how we use metrics. So on one side, again, it's scaling 0, 1, and 1, 0, and the other one is 1 to n, which is left by 2 horizontal autoscaler. The other component that KEDA, the other side of his activity is on the aggregation layer. So what KEDA does is, we said that it is defining a new metric, which is, in our case, is S0 Prometheus. What it does is hosts a metric server. A metric server which will go into, it is exposed on the Kubernetes API, like in the external metrics. So it is actually an adapter that feeds metrics into our aggregation layer, so that it is exposed and available to the HPA controller running as part of the Kubernetes control plane, and so that the HPA controller again can monitor this this metric and take the necessary action, again with the count over 1. Now, what I wanted to talk to you about as well is how we scale basically the data plane. And in my case, I'm using Carpenter. So, like anticipated, Carpenter is a cluster autoscaler, which is different to the traditional cluster autoscaler, because instead of defining multiple managed node groups when you want to use different resource node types, you can actually define the configuration of your nodes with two custom resources, which are the node class and the node pool. So with the node class, you define a few basic parameters which are related to the node itself. So, for example, in my case, it's the machine image, subnet, security group, and the block device mappings. And then we use a node pool to actually reference this node class and define a number of other additional parameters which are a little bit more interesting in relation to the type of resources that we want to allocate. So, for example, we can define the instance family. In the case of Amazon, you can see here that we have a GPU-related instance. We have the instance sizes. We can define the type of architecture. For example, if it is x86 or an ARM architecture, we can also see the capacity type. In this case, I decided to use both on-demand and spot. So I was saying that Carpenter uses these two custom resources to basically define the nodes, the type of nodes that I wanted to generate, that I want my cloud provider to give me. So the advantage I was saying in relation to the using managed node groups is that Carpenter can talk directly to the Node API. In the case of AWS, it's the EC2 Fleet API, which is basically a direct API where Carpenter can request exactly what it needs. So I want this resource of this type, this instance family size, etc., etc. Why is this an advantage? It's an advantage, first of all, because I don't need to define multiple managed node groups and then manage these definitions. It is also, of course, an advantage because Carpenter behind the scenes can look into the current state of my data plane, look at the workloads, and understand if the capacity is a right fit or not. So if Carpenter sees that, for example, there is an over-allocation, or because my compute resources are not used at best for whatever reason, maybe because we are scaling up and down, for example, and we are scaling down, and Carpenter sees that my number of pods is reduced and is not filling the full capacity of my cluster, Carpenter makes some calculations based on internal algorithms and changes the number of nodes. For example, it can replace 2 nodes with 1. It can replace a node with a node that costs less, because Carpenter can also take into account the cost of the instances, and therefore making the maths calculations. For example, this group of pods can be removed from where it is because it costs too much, and we will be replacing, for example, these 2 instances with another instance which is smaller and it costs less. So I was saying that we are using Carpenter for the data plane scaling, while KEDA is taking care of the workload scaling. So to be very clear, whenever there is, for example, in our case of the small application, there is a large number of requests, of HTTP requests, the KEDA will instruct, after having instructed HPA to behave to scale out with the scaled object that translates to the HPA object resource, then the number of pods will increase after hitting the threshold of number 2 requests, and then there will be pods allocated but not scheduled. They will be staying in pending state because there are no nodes. At that point, Carpenter kicks in because it keeps monitored not only the current state of my cluster, but also the number of pods that that are running or could be running, but that they are in pending state because there is no capacity left. So just a couple of words on how Carpenter works from a allocation perspective. This is basically a simple, simplified sequence of steps. The node claim is the entity, the custom resource that represents a request of a node. And the first of all, Carpenter creates the node claim, which again represents a request, and then requests inserts itself to the cloud provider. After the instance is launched, then the node needs to register with the cluster, and then finally the node is labeled as ready. All these states are represented in the state associated to the node claim, and yeah, that can be explored as well while the process is going on. Okay, I think I'm nearly on time, despite the problems that we experienced. I wanted to talk to you about a couple of things more, but well, maybe just one word on scaled object and how the triggers work. So the triggers are reflecting the scalars, so where we want to take the information from, and in the metrics which drive in turn my scaling. We can use multiple. For example, you can see here we have a CPU, and we can mix them as well. So the type can be, for example, from external or from a resource perspective. So served actually by KEDA itself, or exposed by the Kubernetes API through the metrics server. So like I was saying, we can define different triggers, and they are translated, like you see, into horizontal pod autoscaler on the right side, kind of mapped one-to-one. But you can also define the scaling modifiers. So instead of having a kind of a mapping one-to-one to HPA, and HPA, in order to scale, will look at all those triggers, all those metrics, and based on the one that requires the most, will scale the most. This is the general behavior from HPA. What happens actually if you use the scaling modifiers from KEDA is that you can define a formula where you can take the different triggers and combine them with different types of algorithms, so that they are exposed as one to HPA, and HPA can then simply look at that metric and cater itself. I had a small, but shall I?
A few minutes.
Okay. So I just wanted to show you a little bit something more concrete. So this is basically my so like I said, I have a Kubernetes stack deployed into my cluster, again with FluxCD. I just connected to the Grafana, and like you see here, I have current replicas 1 and max replicas 10. This is actually a HPA dashboard. It's out of the box from the Grafana, nothing really custom. So what I wanted to do was basically to show you how a little bit to the what we have at the moment. We have one pod which is running. I'll have the nodes here, just snippets to be faster. So I have two nodes at the moment, basically one large and one X large, two slightly different types, but in any case, we have two. In my definition of my deployment, I exaggerated a little bit with the requests of my resources. In fact, here we can see that I am requesting a CPU of 1, although I don't need it. Okay, I'm going to show you a little bit the state of the cluster at the moment. You can see this is my HPA at the moment. I have 0 as a exposed metric, and the 2 as my boundary, min and max pods defined. I am extracting now the metric from the Kubernetes API server, and I can show you that we have on the external metrics, we have a value of 0, exactly at the bottom here. So basically, I'm querying in the what is the value of my HTTP total requests, which are exposed as S0 Prometheus on the metric name, and the value is 0. So basically, there is nothing going on. Okay, I have my ports now running. already, but yeah, just to be completely sure, I will close them. I will re-forward both, which is both Grafana and my the endpoint that I'm exposing from the internal little application. And I am now loading the application with requests. So because I have a number of requests. You can see that the mean and max is 1 to 10. So I can raise the number of pods from 1 to 10. What I want to do is I want to scale it quite up, and I'm also considering the fact that the number will be averaged by the pods. So I'm loading one pod with 30 requests, which is basically 3 requests on average, which goes per pod and goes beyond the number 2, which is the boundary which I set. So you can see now that the value here is 30. You can see all the pods here that are allocated. Now we have 10. You can see that many of them are in pending state. And if we are fast, maybe I can show you that there is a container creating, a node creating. Well, it's already created. We have now 4 nodes. You can see 2 X large, 1 large, 1 large, and 1 X large. And you can see here that now my current value is raised to 3, again, because we have 30 requests divided by 10, and the target is 2. So therefore, I have a replicas which is now 10. This is the HPA description. Okay, and you can see here basically what happened just now. I'll zoom in a little bit, and you can see that basically the target metric has raised up to this point, and then it goes down, and we have my replicas, which are now like it should be. Good. I think I'm done, and I am over 6 minutes. Thank you very much for listening. Apologies for the inconvenience. I'll let you go to lunch.